Hello everyone, welcome to my channel. In this video, I would like to start up a new module which I've encountered during my first year in the university, and it's called Introduction on Abstract Algebra. So now, before I enter the actual detailed content, I'd like to say a little bit on what it tells me first. So after complete this module, I believe I realized the fact that the manipulations we've done so many years to solve the everyday math problems, they are not taken for granted. For example, if we've got an equation like that, 3x is equal to 27, and then instantly we will say, okay, x is equal to 9. We obtain that by times 3 inverse at both sides of the equation. And that is based on the fact the real numbers with the operation multiple forms a group, which means that there's a multiple inverse in this group. And that's the reason why we can do that like that. Okay, so now let's go into the content of this module. And the very first point I would like to mention about is called the greatest common divisor. There are a couple of theorems related to this concept which prove to be quite useful later on to prove some more higher level theorems in this module. The first one is called Euclidean algorithm. So here's the theorem. If a, b, c, k belongs to integers with b is not equal to 0 and a is equal to k times b plus c, then the greatest common divisor of ab is equal to greatest common divisor bc. This theorem offers you a recurrence relationship. If you want to find the greatest common divisor between two numbers, you can then, at first you are finding a and b, the greatest common divisor of a and b. But if you written down in this form, you can then transfer it into b and c, and then you can do this procedure sufficiently many times until you finally got a true answer. So now let me try to prove this theorem before later on we can use it. From the left to right, if the greatest common divisor divides a, it means a is equal to a constant c1 times the greatest common divisor. So I use g1 to represent it. So a is equal to c1 times g1. Similarly, b is equal to c2 times g1 because this GCD also divides b. Then, since c can be rearranged into the form of linear combination of a and b, you can then substitute the new expression into the old one and happily found that this is divisible. No, on the other direction, g1, the expression included g1 divides c, and that ends the one-side proof. And the greatest common divisor of BC, it is the largest common divisor of B and C. So if you have another divisor that can divide B and C, it is less than greatest common divisor of B and C. And another side is just the other way around, like the same procedure, and also there is a less than relationship. Since both sides need to less than, one side is less than, and another side is greater or equal to. They must be simultaneously obtained. So the only situation that can happen is that these two greatest common divisor is the same. And that ends the proof of this theorem. And there is a fact, by the way, the greatest common divisor of two elements is the least positive integer of the form ax plus by. In this case, xy are both integers. So now, let me come to the next theorem. Suppose that a and b belongs to integers, not both 0. Then a and b are called relatively prime, if and only if ax plus by is equal to 1 for some xy belongs to z. Well, first, I should stress a little bit. When we say a and b is relatively prime, the greatest common divisor of these two elements is equal to 1. This is the basis. And we are trying to prove this theorem. When we encounter such a problem, if and only if, we need to prove for two directions. If there are two statements, P and Q, and we are expected to prove like if and only if, we need to prove that P implies Q and Q implies P, and that ends the proof. So now let me see. From left to right, if A and B are relatively prime or coprime, the greatest common divisor of A and B is equal to 1, I've just mentioned. And then, since it is the form of ax plus by, then we can see that ax plus by is equal to 1, and that is exactly the form in the right hand side. And conversely, if ax plus by is equal to 1, we have seen that 1 is the least positive integer. So that means the greatest common divisor of these two elements is indeed equal to 1. And that implies these two elements are coprime or relatively prime. And that ends the proof. So let me go through another theorem. These theorems, they are both related to the greatest common divisor, this concept, and later on they will have their usages in the improvement of some even higher level statements, like theorems in this module. So now next theorem. If A, B, and C is integers, and A and B are relatively prime, if A divides B times C, then A divides C. You can see that you just expand the expression and then times the C at both sides of the equation and apply the given condition. ACX already A divides AC, and if A divides BC, then these two parts of the expression, they can be written as A times something, no matter this thing is what it is. And then we can conclude that A divides C. And use this theorem, we can prove this theorem, another theorem. So if A, B, and C belongs to Z, the integers, A and B are coprime. And if A divides C and B divides C, then A times B divides C. This condition, A and B are coprime, is important. For example, if, let's say, if 2 divides 4 and 4 divides 4, and 2 times 4, that is 8, but 8 is certainly, it does not divide 4. That is, the reason of that is A and B are not coprime in this case. So this prelude condition is quite important. We need to keep in mind when we are dealing with these theorems and propositions, how it can be used in practice. There are some conditions it cannot be neglected. So here's the proof. C is equal to B times M. And A divides C. We just substitute C in with a new expression. And then since A and B are coprime, this is given by the condition, and apply the last theorem. If A divides BC and A and B are coprime, then A divides C. So now, if A divides B times M and A and B are coprime, that has been stated, then A divides M. That means M is equal to some linear combination of A. And you just substitute it back. And from that, you can see that AB divides C. And that ends the proof. Okay, here are the theorems, some basic theorems related to greatest common divisor. And I would like to talk about one more example, which is also related with the greatest common divisor of two elements. So let's just suppose that you need to go to a supermarket to buy two kinds of fruits, apples and oranges. For apples, the price is 27 pence each, and for oranges, the price is then 69 pence for one. And you are given a task that you need to spend exactly 8.4 pounds on these two kinds of fruits. You need to find all the ways. How can you do that? Well, I mean, sometimes this kind of questions, it has a practical usages. If you are holding money like that, the coins, 8.4 pounds, and you do not need to you need to spend them all. You need to spend them all, and maybe at this moment you need to consider a combination of 2 or 3 or multiple items, how to divide them wisely so that all your coins can be spent all to these fruits. And that leads to a series of equations called linear Diophantine equations, linear Diophantine equations. And in this problem, we need to find the general solutions of this equation. It takes the form of ax plus by is equal to c, where x and y takes integers. We need to find the solutions to this equation. So, in the first place, we should know that under what kind of situations does this equations have solutions, and that leads to the following series. If a, b, and c belongs to integers where a and b are not both 0, the above equations has solutions if and only if the greatest common divisor of a and b divides c. So again, we need to prove this series, and it's straightforward. Nothing to worry about. From left to right, if such a equation has a solution, ax plus by is equal to c, that is the linear combination of a and b. And for the greatest common divisor of a and b, if it divides a and divides b simultaneously, then it divides the linear combination of ax plus by. Since a is equal to the greatest common divisor g1 times something and b is the same, factorize out, you can see that c is equal to g1 times a expression, and that ends the proof of the left hand side to right hand side. On the other hand, if the greatest common divisor divides c, then it is equal to the linear combination of this g1, that's for sure. And then you expand it out. You set, for example, this mk equal to x and nk equals to y, and you then complete the proof. Okay, now so we know that the condition for such a equation to have solutions, and now the next step is to find all the solutions regarding to the equation, and it is given by the following series. If x0 and y0 is an integer solution to this equation, then all the integer solutions are given by these two formulas. K is just a parameter, and G is the greatest common divisor of A and B. And we should prove that first. So the first step is to substitute C with this AX0 plus BY0. Use since X0 and Y0 is the solution, it must have AX0 plus BY0 is equal to C. So you can do the substitution like that. And then you just rearrange the expression and divides just divide G at both sides of the equation. Since A over G and B over G, they are actually relatively prime. Here is a proof. And then you can get what we are going to show. So now let's return to the above example. we need to find all the solutions of such a Diophantine, linear Diophantine equation. These xy represent the numbers need to buy to spend all this 8.4 pound. And the greatest common divisor of 27 and 69 is 3. And then you either by just watch it, or you just reverse the process of Euclidean algorithm, and then you find a combination of ax plus by such that it is equal to the greatest common divisor. And then you see, you just times a factor to both sides of the equation. In this case, the scale factor is 280. And then you find the initial solution. And then apply the theorem we have just proved. This 23 comes from 69 divided by 3. And the same for this 9. And then you just take x and y. They are all greater than or equal to 0 because of the amount you bought. And then the question has been solved. Okay, here is all the content I would like to say in this video. Thank you very much for that. See you next time. Goodbye.